space between the interaction with different nucleus, you have e to the I x dot p, right? X always, this is the distance with respect to the center of mass. X is smaller than the radius of the nucleus, right? All the nucleons are contained in the radius of the nucleon. So when you have x p much smaller than 1, essentially this phase disappears, goes to 0. This is the point. So the phase with which the dark matter particle interacts with all the nucleons is the same. So essentially, a WIMP, so here you can see, for example, in the particular case in which for a mass m, which is much smaller than the mass m, big M of the nucleus, mu is equal to m. And so here you have a typical momentum exchanged. It would be in the MEV. So it WIMPs that are heavy. So, so the characteristic momentum exchanged by WIMPs is such that it is much smaller than the inverse radius. And therefore, 1 over q is much larger than the radius, typical radius of a nucleus. Therefore, the WIMP typically sees the nucleus as a point-like particle. And so its charge is A times its charge. Of course, exactly, it depends. I mean, I'm saying A squared if I'm counting spin-dependent interactions or something that counts the number of events. Could be something that different, right? The properties of the nucleus that the dark matter couples to may be different, as I will point out in a moment. But in any case, there is an enhancement of the cross-section, and that makes elastic scattering to be privileged. This is an enhancement that you lose if you are in inelastic, the nucleus, nuclear inelastic, namely if the nucleus is excited. For larger Q, which are not in the small enough, there is a loss of coherence. So as Q increases, as the recoil energy increases, there is a loss of coherence, and this is taken into account by a nuclear form factor. I will devote a big part of my lecture to nuclear form factors because actually those are essential. This have been from the onset of this type of detection a problematic issue, because you need these nuclear form factors, and they are quite difficult to obtain. There are different ways. There are a few that are measured related to electromagnetic properties, but otherwise you have to rely on calculations, essentially. Yeah. A is the atomic number. So that means the number of neutrons plus the number of protons, if you are coupling with equal amounts of protons or neutrons. Otherwise, it's whatever you are coupling. If you're coupling mostly to the number of neutrons, it would be n squared. So you have this enhancement property of coherent interactions in which you see your target as a point-like particle. No? This is a simple yet effective form factor. The Helm form factor is quite old. It was a way of representing the charge distribution of nuclei. It's a phenomenological, it's a simple calculation, but actually has been fit to different properties, charge radius, etc., of protons, and it works quite well. The only thing is that here we are using it for neutrons too, assuming that the distribution of protons and neutrons is about the same. This is a simple model, and many times this has been used. And this is still in use when other better form factors are not available.
We have this A-squared enhancement only for spin independent, like for scalar vector couplings, right?
Yeah. Yes, for other things, you will have still a point-like nucleus, but of course then you have the total spin and so on and so forth. That's as we will see. Other properties, but still you're looking at mostly the nucleus as a point-like particle, interacting the nucleus as a whole. Yeah. Which usually gives you an advantage in any event. Okay, so the difference between WIMPs and light dark matter started actually when people were looking for light dark matter. So you always had to say WIMPs lighter than a GV, WIMPs that do not produce enough energy in order to be long explanations. So people started using light dark matter as a shorthand for say all this. So what is light dark matter? Light dark matter is one that will not deposit into a nucleus enough energy to be observed by most WIMP detectors. The threshold of most WIMP detectors is a keV. It could be a little lower, it could be a little higher, depends, but it's around the keV. So if your particular dark matter would not deposit enough energy to be above threshold in one of these detectors into a nucleus, then you're looking for collisions with electrons. When you're looking for collisions with electrons, mostly you call these dark matter candidates light dark matter. Otherwise, they could have the same type of interactions, etc. Yeah? It's just an issue of the mass. And so you can see immediately that if you have a mass, for example, of a keV or so, much lighter than keV to GeV, below a GeV, then you will have an Emax that could be in the tens of electron volts. However, this light dark matter could deposit enough energy, maybe 1 to 10 electron volts, in interactions with electrons in different ways, as well as the cartoon I showed, electron ionization or electronic excitation, molecular dissociation. There are many things. And actually, this started to be looked at early on. I must say that this group of Bernabé and so on, the ROM2, did also that in 2007, were one of the first looking in DAMA for an electron signal. And then afterwards, there was an explosion of this type of techniques extended to many other new developments. And there are many. This comes from a workshop 2016, but there are many different ways of looking for electron energy deposited into electron from chemical bonds to superfluid helium, superconductors, semiconductors, etc. I'm going to talk about this type of how do you do the theory part, not the experimental part. You are going to see the experimental part with experimentalists, which is the best thing, actually. With other people. But I'm going to talk about this from the theory point of view, how to compute the cross-section, etc. is quite different, on Friday, the lecture on Friday. So today I'm going to continue with WIMPs. So WIMPs, I would talk about WIMPs before. So WIMPs then would interact, as I said, coherently with nuclear in a detector and produce a nuclear recoil. And you're looking mostly to elastic scattering. I'm calling elastic. I mean, all of this is about elastic scattering. Now, most searches are non-directional, namely, you only measure the energy. But the few that I hope to mention tomorrow are directional. These are less developed. They are not in a multi-tonic scale, and so, but you can extract a lot of information if you have directional information, actually, and you may need a much smaller number of events to gain information from those. In any case, the ones that I'm going to talk about right now measure only energy deposition. And so they don't have directional information. The signature of non-directional searches is the annual modulation of the rate. that I will also talk about. But the rates, unfortunately, now at this point are very small. The energy recoil that you have to measure is really small, and the rates are very, very small. So you must go underground to shield from cosmic rays. Now, there are many of them, and this is a partial list. But if you see, most of the experiments are in settings in the northern hemisphere. In the southern hemisphere, there is only one mine, the Sowell mine, which is really a big cavity in which there are now 2 experiments, but it's not very big. And then there is a very big project that will be a big deal in Latin America. That would be a Gran Sasso-like laboratory under the Andes here. Unfortunately, because of the financial problems that are cyclical in Latin America, this is sort of stopped. This Andes laboratory would have been built together with a highway traversing the Andes mountains. And therefore, the idea was to produce a laboratory in the same way that the Gran Sasso laboratory was produced, just by drilling the cavities at the same time that the highway tunnel was built. The project is already paid for. Everything is ready, set to go, but there is no money. The money would have come mostly, but not exclusively, from Brazil. And the intention was, sure, not dark matter research. The intention was that actually one of the biggest commercial partners for Brazil is China, and it is very costly to pass through the passages that you can use right now, and it would be much cheaper to be able to cross directly from the southern part of Brazil, which is the most developed industrially, directly to the ports in Chile. That was the major economical motivation for this. But as I said, the study is already done. The province already, there's a province here, San Luis, I think, I don't remember. In any case, it would be fantastic from the point of view of physics in general. Why in the southern hemisphere that would be important? I mentioned that the maximum of the rate, I will mention again soon, is in June, at the beginning of June. The maximum velocity of Earth with respect to the galaxy, with the parameters that I show you in the convention, with the conventional parameters that were chosen in 2021, it will be June 2. And otherwise, if you choose a variety of parameters, it's at the very end of December or the beginning of June. It changes a little bit, right? And 6 months later, it is the minimum. Now, this is coincident with the beginning of summer in the northern hemisphere. And summer is associated with having more radioactivity in mines. And this is because of the effect of high temperature in the atmosphere. The upper atmosphere is heated up in summer. It makes it rarer, and therefore pions that are produced in big amounts decay before interacting, producing higher energy muons. So there are higher energy muons. These higher energy muons interact in the cavities and produce different things like radon and bad things. So there is more background in cavities and so on in summer than in winter. In the southern hemisphere, you will have exactly the opposite effect. So if you want to take into account whatever background you may, of course, experimentalists always say that they take into account every single background. I mean, that's guarantee that probably they do. In any case, it would be very nice to have the same annual modulation observed in a place, the southern hemisphere, in which the correlation between summer and maximum number of events is the opposite, right? It will be a very interesting thing to be able to do. In any case, this is why this is Towel mine, but this is very small actually. You cannot do much there. In any case, here you can see 4.5 kilometers, 2.1 kilometers, 2.1. Huh? No, Panda, China is in the northern hemisphere, as far as I know. Yes, yes, yes. As I said, the only one in the southern hemisphere is this one. And it is a big, I don't know if you have seen the pictures of it, it's just a big corridor. That's it, it's a big corridor, that's it. Okay, yeah.
What have towers so far demonstrated?
Sorry?
What have towers results so far demonstrated?
I cannot hear you.
Towers results, what have they demonstrated so far? Are they consistent with the northern hemisphere June maximum?
Nobody has seen any signal of dark matter.
Yeah.
There is no signal. No signal at all. Yeah, that's the very problem. That, yeah.
I was wondering because you told us that the Andes is predicted to in some way simulate what they have done in Gran Sasso experimentally. I think that is done. So in some way, just to be sure, Andes want to in some way reproduce the result that Dama obtained when they claim that they
Not only Dama. In the Gran Sasso, there are many things. There are absolutely many, but it's not only Dama. No, this would be. I will mention Dama. Nobody could reproduce Dama. In fact, there are now several detectors using exactly sodium iodine with thallium doping, exactly the same, and they don't see any signal. So it is really a mystifying what it is. Moreover, Dama has finished now. They have finished. So in any case, this is what I would call an anomaly, because until somebody can reproduce that, there's no way. Okay. The sensitivity has improved enormously. This is a paper in which I am one of the authors. I was the author. I was analyzing the data of the first paper on direct detection. This was 1986. It was 2 years. You can imagine myself analyzing data. But you can get away with it if you are the first, because then whatever you do is good enough, because since you're the first, actually, you don't know very well to do it, but you don't need to do a very refined thing. And actually, so you see actually what it was. The level was a count for KEB electron recoil per kilogram per day, enormous. Now nowadays, it was this is the experiment of Avignone and Brozinski. It was a silicon detector. And I know we are the first, because actually we couldn't, because for other things I never know if this is the first. It's difficult because, but for this we were the first. So much we were the first that we couldn't publish in physical review letters, because we couldn't pass the different reviewers, because there is a model of the dark halo that, of course, was only understood by astrophysicists and so on. There was then dark matter was unknown for many people. There was some modeling of the possible interaction. There was another modeling of what we call then the relative efficiency factor, that now is called quenching factor, which had never been measured then. It was computed. We made a computation. Actually, Steve Allen did a computation of this, starting from neutron data and so on. namely, this is how much energy, how much less efficient it is, would be a dark matter particle to deposit energy than an electron. This was computed. So people objected that we didn't know what this was. And then finally, there was an objection because this was an experiment, an ultra pure silicons, what yes and what not, but to measure double beta decay in the MeV range. And they just shifted the energy and started measuring in the keV. And there was this issue that maybe they didn't know the energy calibration well. This was absolutely maddening, back and forth and forth and back, that finally at some point, I think it was instrumental. I was visiting CERN and I talked personally with one of the editors of nuclear physics. This is physics letters. And I explained and I showed him my record. Everything was done by letter then. It's difficult to believe, but those were letters, right? So I had all these copies of these letters coming back and forth. It was ridiculous. And finally, we published with almost a year of delay. So we were the first, actually. And if you see the paper, actually, there was nothing wrong with it. Now it will be a standard. But this combination of all these nuclear physics, particle physics, astronomy, and the part of going to very low energies with respect to what it was measured, it was new. In any case, I'm sorry, this may not have been so. I'm sorry. It's an interesting story. Eh? Yes, I was I was a postdoc. This was my postdoc time at Harvard. In any case, so this was the first, and then but now, I copy figures from whatever when I have. I mean, when I lecture, I steal. I don't steal. I mean, because I say where I get them from, right? But I use them. So whenever I see nice pictures there, I copy them and I use them. Okay, so this is it is amazing how this is a limit on the cross section and particular, but this is the one home stake, because it was in the home stake mine, right? And they have shielded it with lead from a Spanish galleon that actually they have stolen from some place, radio pure and so on. It was even dangerous being an experimentalist then. And I'm not sure that now you are still stealing old lead from, for example, Roman times, or you're still stealing.
No, I think now you just have friends in Rome and you get it from them.
Yes.
So they're the only ones.
But you don't inquire how they got it, right? Because actually, this is the same thing. You had to go to some fisherman in the coast of Spain and see. But in any case, it was a very colorful type of thing at the time. Okay, so.
It was a Roman galleon, so.
Huh?
It was an ancient Roman galleon.
Yes, that was sunk someplace. And then if it is underwater, but everybody everybody tries to avoid radioactivity, precisely because this is my next thing. Oh, the backgrounds. The only one I will talk about is the background of neutrino nucleus scattering. That's the only one I will talk about. All the rest is for experimentalists, right, to address. But in any case, you have radioactivity in your surroundings. I was mentioning, for example, when muons get to and activate different things in the laboratory. Then internal radioactivity of the detector, that's why the shielding and the pure, radio pure materials. For example, DAMA had their crystals produced underground. These crystals were never above ground because they get cosmogenically activated. So you have to go to serious extremes in order to get radio pure Okay, then of course you have cosmic rays. That's why you must go underground. All the places that I showed are either mines or under a mountain. And then this one, which is the background of multi-ton experiments that I will mention. Okay, the event rate. The event rate is as you learn in classical physics when you have projectiles against the target. And the first thing with how you learn what is an effective cross section, right? So the differential number of events is the number of targets times the cross section times the flux of projectiles, in particular with the speed v, and then you integrate over v. This is the number of targets. As I said, this is the interaction cross-section. Nt times sigma is the total area presented by targets to the projectile. Then the flux of projectiles with speed v would be v differential of number, the number density, how many there are with this velocity coming in. Nv is the flux. And this, you can see, is the number of projectiles reaching the detector per unit time per unit area. So this is then given by a distribution. You have to know your distribution, the particles that are passing through your detector. And then usually this is normalized to 1, so that you put your number density outside, and then you have your differential rate. So this is differential rate in units, typically events per kilogram per keV of recoil energy per day. So this, therefore, the number of targets is, you have to compute it, is the number of nuclides in the detector times divided by the mass, and so on and so forth. You have to integrate from the minimum speed that would be able to produce the recoil energy that you want. For every recoil energy, there is a minimum speed of the projectile that will be able to give you, provide you the recoil energy or larger than the recoil energy that you want, okay? Because this is at the fixed differential. It's at a fixed energy, the recoil energy. Here I have included this delta, which accounts for the possibility of dark matter in elastic. Inelastic in the dark matter, namely the mass of the dark matter particle going out is not the same as they coming in. Not dark matter, not inelastic from the nuclear point of view. It is still elastic interaction in the nucleus, but is inelastic in the dark matter. And therefore, you get the delta there. Now, this n is a number density of particles that are passing through you, and this will be the density, the local density, 0.4, 0.4 or 0.3 if you want GV per centimeter cube, and then multiply by the mass. And this is the local density, the local dark matter density and velocity distribution. This is where your halo model depends in the rate. No? Now, let me mention briefly why inelastic dark matter was brought into the game. This was to favor some materials and disfavor others. This was the time in which some experiments, for example, Dama had a signal, and then others, germanium or xenon, didn't have them. And you could actually select or deselect some properties by tuning this delta. If you put delta equal to 0, this is the usual elastic interaction. So this favors heavy materials over lighter, so iodine in Dama over germanium in CDMS at the time, and enhances the annual modulation amplitude. The exothermic, okay, what is endothermic? Endothermic is delta larger than 1, namely the outgoing dark matter particle mass is larger than the incoming. You have to give enough energy to produce the mass besides everything, right? Besides the collision. And then inelastic is exothermic is the opposite. And so here are
Exothermic means that the dark matter around us is in a sort of excited state, no?
yeah, the problem with exothermic is that you need to make the excited state sufficiently long-lived. Not all of it may be in the excited state, but you should have excited state that is around as a fraction, non-negligible fraction of the dark matter, and then you will have that. And I mean, never underestimate the creativity of theorists to produce models for everything, right? So there are models for all of these things. Yeah.
I have another question. What is the exact state of the dark matter? In here, do we think about the atomic dark matter? So, I mean, what is I don't understand what is the exact state and exact state of the dark matter.
Could be excited or could just be higher mass. For example, if you have a pseudo-Dirac, pseudo-Dirac is 2 Majorana particles that are one slightly more massive than the other. There is a split because it's a small Majorana mass. If the Majorana mass contributing would be 0, they would have the 2 Majorana would be degenerate and they would form a fermion, Dirac fermion. So it is either excited or just higher mass. So it could be that actually you have a mediator and the mediator necessarily couples to the 2 Majorana and you can go from one to the other, but you cannot go to the same. Okay? And so it is higher mass. Excited state, it's a way of talking. Higher mass. Okay.
This related with, because I saw that some papers that are mentioning upscattering.
It depends what it means, but if it is up scattering or down scattering in terms of mass, yes. Yeah. Yes. Up means simply that you increase, but you have to say what you increase. If it is the energy, if it is the mass, if it is what. Or down scattering, but vice versa, but it's the same. Okay. So, so this is the, unfortunately, in this plot, this is the recoil energy, this is V mean, and here it is, you have the velocity here and the recoil energy. But it is the type of kinematics that you get is actually very different. Now, for example, here you have the recoil, what is V mean as function of ER. This would be for endothermic. And you can see very well that you have practically, you need enough energy in order to produce the higher mass particle. So all these lower energy events are not there. They are forbidden, kinematically forbidden. In the other, actually, it is preferred that you will go to a very low recoil energy. So the kinematics actually is quite different, and you can favor one or the other. I'm not going to enter into more details, but if you want, it's just I wanted to mention what is it was mentioned before actually what inelastic was. And by the way, yesterday I did something also. There was a question, another question there was about how lumpy could be the dark matter and still have a density, the dark matter density in the galaxy, which is 0.4 GeV per centimeter cube. Okay, what I did was the following. I took the volume of the solar system. Well, the volume up to Neptune is about 30 astronomical units. You can do the same thing. You take this to the cube. You see how many parsecs they are. And then you take what is the energy that contains. You multiply rho by this volume. And what you get is about, if I did it correctly, 10 to the minus 13 solar masses. So if you remember, I mentioned that it is still possible for primordial black holes in the range, the asteroid mass range, which is 10 to the minus 10 to 10 to the minus 16 about solar masses. 10 to the minus 13 solar masses is a perfectly allowed candidate in PBH, primordial black holes, to account for the dark matter, and you will have one of them within the volume of the solar system. This is your question, refers to your question. So one primordial black hole, 10 to the minus 13 solar masses, if my calculation is good. I think 10 to the minus 14. In any case, could be 10 to the minus 13, 10 to the minus 14. There will be one for all the volume of the solar system. And this would be enough, actually, to account for the dark matter. Okay? So yes, you may find that actually, if it is not particles, you may find actually that there is only one primordial black hole. Okay? If it is heavier, it will be only a fraction, namely part of the time is inside. You will not find even one.
There's even a word, I think the author doesn't stand behind it anymore, if I recall correctly, that says that planet X, this theorized planet, may have been a primordial black hole, but I'm pretty sure I remember talking to the author, he said that it no longer is.
Well, no, but there was a question of how lumpy it could be, and still the measurements would be fine. So you could have one of these objects per solar system and be perfectly fine or less than one, and be perfectly fine to be candidate for dark matter. So this was the question. Okay, otherwise I would forget to mention. Okay, so let us continue now with the cross section. Usually, when you have a cross-section that is like a spin independent and a spin dependent, those are the only ones, that is momentum transfer and velocity independent, then the differential cross-section has this form in which there is a constant, a bunch of constant, 1 over v square. So if you put, this is the speed square. So if you put here the speed square, the 1 over v square cancels out with the v that comes from the flux of incoming particles. And then you have this characteristic integral, f of b over v. And this integration over velocities then goes directly to a function that here I called eta. In the literature, some people call it g of E mean or eta of E mean. I always use the eta of E mean. And this would be then where the eta of E mean multiplied by rho, the local density, is where the model of the halo enters. And so you need, in order to, so in this cross-section, you single out a reference cross-section many times. Can be chosen to be the cross-section with a proton instead of a nucleus with a proton, okay? But otherwise, any would do while you define correctly. This is a constant. And then you make a plot once you have given a local density and velocity distribution model. You compute this part, and then your limits, you give your limits in the usual way, cross-section, reference cross-section as function of the mass. And this is what I call halo-dependent analysis, because you have to provide a model for the dark halo. Okay, and so tomorrow, I hope I will introduce you to halo-independent, in which you actually derive eta, starting from scattering. Instead of providing eta, you take out eta, okay? You extract this function eta, okay. Now, this is not what you directly measure. In any experiment, what you measure is not the recoil energy directly, but a proxy for it. It could be a number of photons produced by photomultipliers, right? Or it could be some ionization, could be some, in electron equivalent energy and so on and so forth. Namely, some signal in the detector produced by the recoil. But always there is some uncertainty, and you have to give this energy resolution function that comes from your detector. You have to understand your resolution function. And here there is an efficiently cut, it's called cut acceptance also, below which you have usually too large a background in order to measure accurately. And so you cut your data. So and then you have you measure something E prime, you have your rate as function of your observable energy, and then you integrate over this, that gives you the probability with which E prime corresponds to a particular energy E, and you integral over the R. This is how you compute the observable rate as function of what you can observe, which is this energy, this proxy energy. This gives a series of complications, of course. First of all, you have to understand very well what is the detector response. I don't have anything really very valuable to say about that. And moreover, you have experimentalists that can tell you much better how you do that. But then there are uncertainties in the cross-section. There is uncertainty in the halo model. Okay. So 10:30, right? So I have. Can you please tell me 5 minutes before? If I forget, thank you. Yeah. So okay. So the detector response, well, I don't know. As I said, I don't have much thing to say, but these are, you have to measure. For example, your quenching factor I mentioned when you have crystals, or this scintillation, relative scintillation efficiency. If you have, you produce light, it's your S1 in liquid xenon or liquid argon, or things like that. So, and there are various ways in which you measure. Usually you measure either phonons, you shake your lattice and it produces some phonons. If you wait long enough, these phonons actually transfer into heat. You can measure it to heat. You can produce photons, light, or you produce ionization. This is it usually. There is a much nicer I told you that I copy, right? So this is a very nice, better version of this very old that comes from a fantastic, very, very nice review here, recent review actually. Yes. But in any case, I use their figures. Yeah. I use all the figures that this is a very nice figure. So, nowadays most experiments use 2 of this because it allows you a better discrimination with backgrounds and stuff like that. So I leave this issue to experimentalists. So let us go to cross sections. So cross sections is where your input, besides the mass, this is the input of particle physics. So how does the dark matter particle couple to the nuclei that you are using? There are 2 types of dark matter baryon models. In one of them, you just phenomenologically can start with couplings directly with protons and neutrons. Or you start with fundamental interactions. So you usually, if you are looking for whatever signal there could be, you can proceed in this manner. If you are instead trying to test or search for a particular dark matter model, ab initio, ultraviolet complete, right, with a Lagrangian that couples to fundamental particles in the standard model, these are quarks and gluons, then you have to start from there, and then you need to pass from these quarks and gluons to nucleons, and then from nucleons to nuclei. In any case, always you need to pass from couplings from nucleons to nuclei. Now here is, there are two that are the most used experimentally, actually, in order to present data, which are spin independent and spin dependent. Spin independent is a coupling due to a scalar mediator or a vector mediator. In the non-relativistic limit, you have, it transforms into a coupling that is just one. So you're counting essentially the number of particles. But you can have a different coupling with protons and neutrons. Z is the number of, is the charge, the number of neutrons. A minus Z is the number of, Z is the number of protons, is the charge. A minus Z is the number of neutrons. And for P different from N, it's called this kind of, okay. Isospin conserving is Fp equal to Fn, but you could have isospin violate. Why isospin? Because the isospin P and N are a doublet of isospin. So an isospin is conserved. They're essentially the same particle. You have to have the same coupling. So isospin conserving or isospin violating. This isospin violating, again, was introduced phenomenologically because since this nuclei, the line of stability of nuclei bends in this way. This is the number of neutrons, n, and this is the number of, n is A minus Z, and this is the number of protons in a nucleus. And you can see actually that it bends. So the number of neutrons and protons is different progressively. When you have heavier and heavier nuclei, they are more neutron rich. So by picking up particular ratios of these couplings, you can disfavor, for example, maximally xenon. Practically, you can make the xenon coupling 0. Not exactly because of the isotopic composition. So you can make 0 one of the isotopes, but not exactly the others. However, the coupling is minimal. By picking another one, you disfavor maximally germanium, and so on and so forth. This is phenomenologically dictated. And again, there are limits. There are models for this kind of thing, as an example. The other is the content spin-dependent interaction. Spin-dependent interaction comes from a coupling that is axial vector, gamma mu, gamma mu, gamma 5 coupling. And again, and now here you have these form factors that they are the form factors of the spin carried by protons and carried by neutrons, and you could have different couplings, A, with the protons and neutrons. This is in general what it is. So again, in order to have any response from a nucleus, you have to have a non-zero spin in the nucleus. Argon has 0 spin. So in principle, this kind of cross-section is 0 for argon. But for others, it depends because you can have you have unpaired protons, namely the spin is mostly carried by protons, or the spin is carried by neutrons. These are different types of materials. So you can favor one or the other, having different AP and AN. And moreover, there isn't the isotopic composition. Here, for example, xenon has in total about half of the xenon in the normal isotopic composition has a spin. It is much smaller instead for silicon, and so on and so forth. Now, experimentalists mostly use isospin conserving spin-independent and spin-dependent interactions to give limits. This is some example. Maybe it's not the latest, because I can see that actually I didn't look for the newer ones, but these are from the end of last year. Maybe there is some. I don't want to offend any of the experimentalists here who may have produced a much nicer plot in the last few months, right? But in any case, so here you have this. This comes from Panda X and from LZ, and here of course there are different uncertainties in different ways. But these are this. I would like to use this plots in order to indicate that why the shape of the exclusion plot is like this. Right? The shape of the exclusion plot depends here. It depends on the energy threshold in your detector. And then this asymptote goes as 1 over the mass. So this is as function of the mass. So it goes as 1 over the mass. And how high this is depends on your exposure. More exposure means lower. Okay? So the left boundary, given a WIMP speed v, then the maximum recoil energy, I gave you the equation, is 2 mu v squared. So that means that the threshold would be equal to a certain mu minimum if you take the maximum velocity. Remember that the maximum velocity with respect to a detector is the escape velocity plus the velocity of the sun, essentially. So it's about 800 kilometers per second with the choices that I showed you in the convention of 2021. And then you put that Vmax, so it depends on your Vmax. What is the minimum reduced mass that you get? In the case, for example, in which the mass is much smaller than the mass of the dark matter particle, much smaller than the mass of the target, then mu, the reduced mass, is the mass of the dark matter, and therefore you get to the minimum of the mass. So the minimum of the mass that you get here is directly related to your threshold, the threshold, experimental threshold. Then the exposure, the number of events times is proportional to the exposure times the cross section. Okay, and this is, of course, you get an upper limit. This is for upper limit. You get an upper limit. This is smaller than a fixed number. Therefore, exposure times sigma minimum is equal to a certain fixed limit that is given precisely by your upper limit on the number of events of dark matter that you can measure. So sigma decreases as the exposure increases because this product is fixed. Okay. And then finally, the right boundary. The rate is proportional to the number of dark matter particles around. The density is fixed, is 0.4 GeV per centimeter cube. And so the number density is the density divided by the mass. And so at some point, this dominates the rate because dark matter become too rare and decreases as 1 over m. And this becomes then the cutoff, the type, how the plot cuts off. So you always see this sort of half moon or what, yeah. So this curve continues forever. So yes, so this is dark matter. I'm sorry because these two things are too close. I should separate them. This is the dark matter mass in GeV. This is the label for this. So this is 100,000 GeV. And this is the sigma in spin independent. So this is precisely this plot.
So this is the bound.
And this is the... Right. This is the explanation of why these limits that you see all have this shape. Okay. Now, here you have some limits, but if you wonder what happens at higher cross sections, There are other limits on higher cross-sections. They correspond to WIMPs which would not reach your detector because they would be either stopped in the upper atmosphere or in the crust or whatever. They don't reach your detector. Or if they reach your detector, they would interact more than once. And usually you throw out those events unless you search for them specifically. And so here is a different type of limits. Again, I took this from a very nice collection of all these limits, actually, that they have been in the literature, but in any case, they are collected here. Okay. And these are the same type. You see that here the value of the cross-section, here is different, 10 to the minus 43, 42, and so on. This is 10 to the minus 40. They are different this is for interaction with protons, with interaction with neutrons. And in this analysis, you take one of the AP or AN equal to 0 and analyze only the other one. Okay. These are not the only type of interactions. I mean, there are many. Here you have some long list. I don't expect that you would see all of this because it's very small. This comes, for example, here you have the reference. This is written directly in terms of N, couplings with N. Here you have a few bigger ones, okay? And so you have the relativistic operator and the non-relativistic limit for several. For example, here is this scalar mediator. This is a vector mediator. Both of them go to 1, 1. This is the coupling. Pseudoscalar with gamma 5 in the middle. It goes to q dot s times q dot s. Axial vector, here you have gamma mu, gamma 5 goes to s dot s. I made an example later on how you get the non-relativistic limit, but usually it's understood. So, and of course, and here there are more. 4, of course, you could have a scalar dark matter. And people consider also vector dark matter. So these have been classified in the type of interactions that you can have. You see that here you have eliminated the potential propagator. The propagator goes outside and you leave only the interactions terms. And this is what you do in effective field theories. So this is where we are heading in a moment. Each different nuclear coupling needs its own form factor. And this has been a thorn in the side of every theorist or experimentalist since the beginning. Because you need to know what the response of your detector is, right? Now, the mediators could be heavy or light with respect to the characteristic momentum. Namely, for heavy, you just take the mass much larger than the exchange momentum. For light is the opposite. So the propagator becomes 1 over q squared only. Okay. And the cross sections can be very different. So here you have the cross section for, this is the spin independent with equal coupling to protons and neutrons. And this is, for example, a coupling of a magnetic dipole coupling. Entirely different. You see that here, this is independent of Q. This Q reference is just a reference cross. Usually, I don't know, you have to give a value, but this is a constant. It's not actually, it's a value. So, this is the momentum transfer. So it can be very different. For example, here you have different ways. So this goes to 0 as Q goes to 0, as the energy goes to 0, right? So these are this type, okay? And then others, but you can see actually, this is in xenon, this is for the mass of the dark matter particle, 50 GeV, the same in all three. And this is for xenon, for germanium, and for iodine. Now, this I mentioned already. When you consider only the couplings, it's like having considered a heavy mediator, and then extracting the propagator becomes a constant. Now you say, well, but what about if it is light? Well, if it is light, phenomenologically, any mediator of dark matter interactions cannot really be strongly interacting. So it doesn't affect the response of your nucleons. And so if it is not strongly interacting, it doesn't affect your nucleon, then you just put it outside and you change whatever amplitude you computed, you replace it by a long-range interaction. This factor will multiply to the square in the cross-section, and that's the strategy. Now, there are many different ways of going about in computing form factors, nuclear form factors. I will mention only two: non-relativistic effective field theory and REFT, and chiral effective field theory. And a good reference for overview of all current EFT approaches is one of these snow mass processes white papers. They're very useful for that. And actually there is it has like 10 different authors, but all the big practitioners in this type of subfield are represented here. And it's a very good overview. But I will mention only two. This is starting from nucleons and going to nuclei. And actually, it provided this type of calculations in the program, in particular, Anand, Fitzpatrick, Haxton have a program. All of this is implemented in programs. I didn't mention the programs. They are all implemented in programs that you hook up and connect in order to compute different things. 5 minutes. 10 minutes. This is 10. Okay, that's in any case. So these are non-relativistic. You see that actually both the dark matter and the nucleons within a nucleus are also non-relativistic. The characteristic momentum is, the characteristic velocity is 0.1 c. So they are both non-relativistic in both terms. And therefore, you use non-relativistic physics and quantum mechanics, non-relativistic quantum mechanics, essentially. So these are Galilean invariant quantities. Galilean meaning that if you have a velocity 1 and the velocity 2, so something that is moving with velocity 2 carried by something with velocity 1, the final velocity v1 plus v2, non-relativistic composition of velocities. And then you have three quantities that are invariant, which is the momentum transfer. This is a way of parameterizing. You could use the momentum transfer. I'm using this dimensionless quantity divided by the mass of the nucleus. And this V is dimensionless, is one. Here you have another dimensionless quantity, which is the component of the velocity, the relative velocity perpendicular to Q. And here are the spins of the dark matter particle and the nucleus. And with that, you produce you have a total of 15 different operators in which you see the propagator is removed. You leave only these effective operators. Then you make a series of manipulations that nuclear physicists are best at this. I still don't understand everything they do, actually. As soon as I understand it, I forget it again, I must say, because it's quite, for nuclear physics, this is obvious. And then you get these form factors, actually. So for the usual things, you get 6 form factors. And these form factors are tabulated, and many, many people use them because they characterize different types of interactions. All right. So some people use in their analysis separate EFT operators. I don't think that this is the best. But here, for example, there is a recent paper of LC. There are 15 of them. I mean, these are just a few. Taking one and then another and then another and then another as your model for the dark matter. However, if you start from, here it is. So you can start for relativistic Lorentz invariant, which is what I used before with gammas, gamma mu, gamma 5, and so on. This is how we operate in particle physics, right? With the Lagrangian and relativistic, and then we take the limit. And so, for example, if you take the limit of this gamma mu, gamma 5, you go through, Bjorken and Drell type of physics, if you still use Bjorken and Drell. Bjorken and Drell was my thing, and I still use it. So in any case, you get this operator. And this operator here is proportional to 0.4. So some of the interactions actually some of these interactions that you can write Lorentz invariant interaction go to just one of those. So if you choose one or the other, they differ by a constant at most. And this happens with many, but there are others that don't. And if you consider only separately, you are neglecting interference terms. You see that actually, for example, in this case, each of these operators is multiplied by coefficients that depend on the particular target. So if when you're comparing the results from different targets, these coefficients enter in different ways. And you may be losing that while one is dominant, one of these terms is dominant in one particular target at a particular range of energies, another one, but stemming exactly from the same dark matter interaction, another one could be dominant in a different target. I have 5 minutes.
Sorry, the operators, the relativistic operator are generated at a very high scale, no?
No, just a moment. You can do relativistic operators with nucleons. This is what I have been talking about.
Okay.
With nucleons, right? You can start with, if you don't know what your dark matter is, but you know that your mediator is pseudoscalar, you can write that when I haven't passed through the complete ultraviolet, which this is the next plot, exactly. This is the next, exactly. Okay. So this is, I stole this from Hoferichter. Yes, it gives I didn't put it here, but it is actually, it's stole. As I said, I steal diagrams that I like in particular. Yes, so so what happens when you have, a ultraviolet complete theory in which you really couple that. For example, this happens when you analyze supersymmetric models, for example, or other models that are to give you a complete coupling with the standard model. And then you can use actually BSM at different scales, integrating out, as people say, actually considering heavy, making the limit of this heavy. First, whatever in maybe mediator is heavier than the W and the Z. Then the W and the Z. And then quarks, the top quark, the B quark, and so on, they all become heavy. And they drop out, they go to the limit of large masses and so on and so forth. The aim of doing all that, first of all, you remain an agnostic to fundamental interactions because several different mediators, for example, it could be a mediator in the S channel, it could be a mediator in the T channel, but when they are heavy, all of them end up in the same contact interaction. So remain agnostic about fundamental interactions once you are computing your detector response. And also make contact with accelerator and indirect dark matter searches, which use also effective couplings. So in order, if you want to do that, then you have to start with fundamental interactions and go through this tower. Now, here in the last tower is where chiral symmetry comes on. This is the EFT approach at the level of the LHC. You start, therefore, with all of these different couplings between quarks and gluons. This is a classification of all the pure possible quarks and gluons, 10 for the quarks and this for the gluons. Then you do exactly the same, heavy mediators or light mediators if they are not color dependent. Then you write an expansion in these operators. And then you pass, and this has been done since the 1970s onwards. It's already, sorry. At the time. You were pointing at the time. I was saying, what is he pointing at? I would have said, yeah, I'm finishing in, let me say. Okay, I'm going to finish in there, one more, and then we finish there. Okay. All right, so then these operators induce effective Lagrangian at the nucleon level. And you have to do a lot of work in order to pass through that. You have to know QCD, you have to know different things. Chiral effective, chiral EFTs is a branch of nuclear physics at the contact between nuclear physics and QCD. That have been developed by a bunch of different nuclear physicists. They have done very pretty things unrelated to dark matter, and a lot of them related to dark matter too. And in them, so while the approach that I had before had only nucleons in them, here in this approach, you incorporate also pions, and maybe pions and kaons. And you use the chiral symmetry properties. You know that in QCD, because up, down, and strange are relatively light with respect to lambda QCD, you have a global symmetry, which is how quarks were discovered, actually, which is SU3, a chiral, SU3 left cross SU3 right, and cross U1. Okay. So you use all these properties of pions and so on, and they have had an enormous success in doing all sorts of things. So they improve the coefficients. First of all, they provide a systematic power counting scheme to organize WIMP nuclear interactions. They include pions too, not only protons and neutrons. They improve the coefficients that are used in the expansion in non-relativistic operators. Sorry, this should be N, not M, non-relativistic operators. They go beyond the effect of two particles. They can include multiple particles in particular. So they can include two particles. So WIMP interacting with two nucleons at the same time, right? Instead of just one by one, which is how this is done so the non-relativistic EFT uses the shell model, where there is a frozen core of nucleons surrounded by valence nucleons, which occupy energy and angular momentum states in close analogy with atomic electrons. And then the degrees of freedom include only nucleons and one particle interactions. These are the approximations that this non-relativistic EFT consider. Here you expand and include even WIMP, virtual photon and in fact there is a paper by, I think, Laura Baudis, right? In which you have, or maybe there is a combination. mistake some people who work together many times. Is you the one who were in this limit on pion, WIMP pion limits with Xenon? With these guys, Hoferichter and so on. Yes, so they have done very pretty things I'm not going to mention anymore. I think at this point, this is all I will say. I think it has been pretty good. And I will start now with the neutrino fog and how having different type of interactions actually makes the neutrino fog more or less easier to overcome. This is what I will start next. So I'm sorry I extended a few minutes. We started late. We started like 10 minutes. In any case, it doesn't matter. Questions?
Other questions?
You say like in the last part a lot of like the interaction and how the coupling occurs, but all the sorts of detection we are forecasting and trying to have, like they see only the recoil. So from the recoil, can we infer back on the interaction and the propagator?
Huh. Yes.
For example, like here that before we see something.
You may in different ways. Once you have a signal, you should have a signal in more than one experiment, or at least but there are some that are actually clever, and in the same experiment they have different targets, very different targets, like CREST, for example, that has several. So if you can extract your signal with different nuclei, that gives you a handle. If you can measure, as I will mention next time, you can measure the annual modulation, you have another handle. Well, if you have a different velocity, you have several terms with different velocity dependencies. It will be very different. In different targets, it will be very different your annual modulation than if you have just one term, 1/v term, right? Depending on you have multiple velocity dependent, but it will be a very nice problem to have. But you will need different targets, because then you will realize that in some of them you see something, some of them you see very little or nothing. That gives you already an indication. If the coupling is with all of them, it couples with one, namely to the number, or it couples to different properties of different nuclei. But it will be a collective effort to try to see what it is. In last instance, yes, you can have a handle on what it is, but through combining data from different experiments. If you only have one, that's why even at the ultra multiton, you're pursuing two. One is xenon, LC, and so on, and then argon too. I hope it will be pursued too, at least. We'll see.
Can I ask you something about this last comment? So these two models that you present are two models of like the nuclear shells.
So these models are really very simple.
For every dark matter, you said at the beginning, I'm interacting with just I'm counting number of targets.
Well, no, that depends on the type of interaction, not how heavy it is. It depends on the type of interaction.
So if you're spin dependent or stuff like this.
Yeah, these are all, these are all different types of interactions, right? So let me see it back again. So here, actually, there was this neat, I used at the beginning, this one. So you see here, if you make your model Lorentz invariant relativistic operator, okay, or this one, this is bigger, that's why I put it.
I just don't, so the back of the envelope that I should have in mind is that the momentum exchange is, say, with the nucleus, with the whole nucleus.
with nucleons in this case.
Nucleons then I don't see because it's
Yeah, nucleons.
one GeV.
Yes, this is the nucleon. You have extracted here with a nucleon.
One GeV times 10 to the minus 3
It-
is
it-
less than the pion mass. Is an MeV.
yes, they are all the max. 200 MeVs would be the maximum. People say yes. 200 MeVs or below 200 MeVs is
How
what.
can I see single pion? I mean, it's very weird. I mean, the quantum scatters on larger scale.
These are all, well, she will know better than me, but these are all virtual pions. Now, how can you extract the signal for virtual pions? Don't ask me because I do not know. That's why you need this nuclear physicist to tell you, because sincerely I have no idea. But there is a kinematic cat that you have to do for sure, right?
But they will all look like contact interaction because I'm at a scale that is much larger than the pion mass.
Yeah,
Unless you
what they
make it
found-
matter fast.
I mean, if I remember, what they found is that for independent interaction, these like two bodies,
The two body, exactly. Right.
the structure function for independent.
Yes, so it goes beyond the one particle interaction. Here you are summing as if, you're summing the amplitudes, but you're summing one interaction. But instead you have in the chiral effective theory, in this very neat, here you have, okay, something like this.
Oh, well, I would have to look at maybe we can stop the point.
Yes,
Discuss over
I'm not the best person for this because sincerely I have a difficulty reading all this literature. You really have to be a nuclear. Moreover, they have all these names for different things, resonances, things like that, that for them is very clear, but it is bit obscure, sincerely, right? They have all these names for different things. It's rather not trivial. Okay, sorry. Some people want to go to have coffee already. And they were here from the beginning. So that's okay. Thank you.